Donc, bon après-midi. Good afternoon, everybody. So I am Caroline Nord. I'm professor at Université Paris-Saclay. And I will be sharing the dissertation committee of Thomas Padioleau today. And then after the presentation by Thomas of about 45 minutes, I will allow different people to speak. First of all, that will be the first reviewer, Anne Algren, from Lawrence Berkeley National Lab. And then that will be Philippe Eluy, who is also a reviewer of the dissertation. And then that will be Isabelle Baraf, who is professor at Université d'Exeter. And then there will be Carlos Pares from University of Malaga, who is also professor. And then I will be the fifth to talk as a non-specialist of the subject, because I don't know anything about compressible fluids, so I've learned a lot of things here. And then I will give the opportunity to talk also to the people who work with Thomas and who advise his thesis. And then maybe I won't forget to give the possibility to the people in the public to ask a question. All right? So, Thomas Padioleau, you have 45 minutes to present your work. Please.
Thank you. So thank you for attending to my PhD defense. So I will be presenting my work about the development of all-regime AMR simulation methods for fluid dynamics with two applications in astrophysics and in two-phase flows. I have been supervised by Edouard Rodi, Pascal Tremblin, and Samuel Koch. So the two applications in astrophysics and two-phase flows have in common to be based on hydrodynamics models, meaning that we aim at studying the time evolutions of quantities such as the density, the pressure, or the velocity of the flow. This flow can be characterized by a dimensionless number, the Mach number, that is defined to be the ratio between the local material velocity and the local speed of sound. As I said, this number can be used to characterize the flow from the low Mach numbers with a flow near incompressible to larger Mach numbers with compressible effects. In situations exhibiting a wide range of Mach number, either in space or in time, these can be quite challenging from a numerical perspective. We can run into these situations in astrophysics, for example, in the interior of stars, in the convective zone, in which near the core, the flow is at low Mach and at higher Mach near the surface. In the context of two-phase flows, for example, using liquid water, even at a low Mach situation, a small velocity jump can trigger large pressure waves due to the stiffness of the equation of state. We aim also at performing more realistic simulations, and we need to, in order to use to do three-dimensional simulations, we need to use dedicated computers called supercomputers, facing the issue of the performance on these various architectures. So this raises different questions: how to deal with simulations exhibiting a wide range of Mach numbers, so all-regime situations, how to deal with the performance and the diversity of architectures in supercomputers, and more generally, how to improve the time to solution, meaning the time needed to get to the numerical solution. This work takes place into the framework of a code called ARC, standing for All-Regime Cocos. That is a fork from a code called Euler-Cocos, developed at Maison de la Simulation by Pierre Castanet. So in order to answer these questions, my work and this presentation are divided into two parts. The first part will be dealing with the design of robust numerical schemes, aiming at simulating a wide range of Mach numbers. In the first section about the astrophysics context, and in the second section in the two-phase flow context. In the second part, we will be addressing the performance issue. In the first section about the parallelization of the code called ARC. And in the second section about a more algorithmic point of view in order to accelerate the time to solution using hybrid spectral finite volume methods. So let us first begin with this astrophysics application. So in order to introduce the numerical difficulties that we may face, we use this example, which represents the simulation of relaxation shocks during the formation of a star. So we have the core of a star information that is accreting matter with the tracer particles here represented in black points. The velocity, the radial velocity is here represented in color. And we have the situation is at a near hydrostatic equilibrium inside the core in a low Mach regime with compressible effects due to the accretion of matter near the surface. In order to study the convection, we have different approaches possible. A first approach is using dedicated models called so near compressible or low Mach asymptotic approaches. They filter the sound waves, and from a numerical point of view, this is attractive because it gives a relaxed CFL condition, stability condition. But in order to simulate the previous situation, we would like to use a more general approach using compressible models. So these models are based on conservative equations, so the Euler equations with gravity source term. They are usually discretized using finite volume methods, so for example, a good enough type method. And this time, the CFL condition, so the stability condition, involves the fastest wave speed in the system. So in this case, using the speed of sound. This raises different numerical difficulties. The first one is related to this speed of sound. If we take a uniform and low Mach situation, we need to do a lot of time steps in order to study the time evolution that is of the fluid that is related to the material velocity u. Because of this decoupling, this raises a difficulty. Another difficulty is related to the source term and some particular solutions, so called equilibrium states. In the case of a naive discretization of the gravitational source term from one part and the hydrodynamic system on the other part, we may end up with a numerical scheme that is not able to preserve these states and leading to a loss of precision. And finally, it has also been shown that for such numerical schemes, so for example, good enough types, collocated schemes, we may face a low Mach inaccuracy, meaning that in a low Mach situations, these numerical schemes exhibit a large diffusion, and again leading to a loss of precision. So we aim at designing a numerical scheme that answers these difficulties. So before deriving the numerical scheme, let us first introduce the Euler equations that I've been mentioning with the gravity. So the Euler equations are based on conservation principles. So the conservation of mass, the balance of momentum, here written with the gravitational source term using the gravitational potential phi, that is here stationary. And using this stationary potential, we can derive a conservation on the mechanical energy that is defined to be the usual total energy from the Euler system, so from the internal energy, the kinetic energy, and the gravitational energy. And to fix ideas, we also use an ideal gas equation of state. We also define some particular solutions of these equations called hydrostatic equilibrium solutions. So they are defined to be at rest and stationary solution. That is equivalent to say that the pressure gradient is exactly balancing the gravitational force. And for the particular case of these solutions, the energy equation is not playing any role. And so we want to have a discrete counterpart of this equation. And finally, before going to the discretization of these equations, we need to introduce a relaxation on the gravitational energy. So as I mentioned it, by combining the conservation of mass and the stationary potential, we can write an equation on the gravitational energy, rho times phi. You may notice that the gravitational energy is depending on time solely due to the density variable rho, contrary to the new equation that we introduce. So we also introduce a new variable psi that is seen as an approximation of the stationary potential phi, and that follows this equation. And in order to recover the stationary potential phi, this equation has a stiff source term with a time scale lambda that is, in the limit case of lambda tending to 0, we recover the stationary potential phi. So we use this equation along with the Euler system to discretize the system. So we adapt here an acoustic transport operator splitting. So the idea is to decouple the fast phenomenon from the acoustic phenomena from the material velocity by splitting the flux divergence into transport terms in red here, and acoustic terms in blue. So this leads to 3 subsystems. From the blue terms, an acoustic system. From the red terms, a transport system. And finally, a relaxation step in order to recover the stationary potential phi when lambda tends to 0. So to discretize this system, we need to provide 3 numerical schemes. In the case of the acoustic system, we use a Riemann solver based on a Suliciu-like pressure relaxation. It introduces a new pressure, pi, that is an approximation of the thermodynamics pressure P. In the case of the transport subsystem, we use a standard Apuy numerical scheme. And finally, in the relaxation step, we tend lambda to 0 in order to recover the stationary potential phi. The numerical schemes write in this form. So we notice that it is conservative, respectively, for conservative equations. That was not obvious from the derivation of the numerical scheme. We write here the 2 fluxes, so the velocity flux and the pressure flux coming from the acoustic step. We notice that for the case of the velocity flux, we have a new term in red related to the gravitational source term that will be necessary to have well-balanced numerical scheme. And in the case of the pressure flux, we introduce a parameter theta in front of the diffusion term that is here to rescale the diffusion term and to fix the Lomack inaccuracy of such numerical schemes. In the case of hydrostatic equilibrium, we have a counterpart, as I said, of these solutions. If a solution is initialized in this way, meaning at the velocity is 0 and the pressure gradient between 2 cells is following this equation, due to the term in red in the velocity flux, it vanishes the diffusion term. And as the solution is also at rest, we have a 0 velocity flux. It can also be shown that the pressure gradient in one cell is exactly balancing the source term, leading to a stationary potential. That is the definition of a well-balanced numerical scheme. So we run different simulation, different test cases. So the first test case is the stationary glacial vortex. So in this case, there is no gravity at all. So we have 2 numerical schemes, a standard Godunov type scheme and the Euler regime scheme that we previously derived. And we represent here the velocity field. So in the case of standard Godunov type scheme, for a fixed resolution, a fixed grid, if we decrease the Mach number, which is a parameter of this test case, we observe that the vortex is destroyed and gets aligned to the grid. In the case of the all regime scheme, due to the low Mach correction, we are able to recover this vortex. Because we are using a compressible approach for convection simulations, we are able to perform strongly stratified Rayleigh-Bénard instabilities. So here we represent two convection cells, and in color the Mach number field. We observe that in this case, because of the strong stratification between the upper part and the bottom part of the grid, we have a large Mach number ratio. So near transonic flow at the upper part and a low Mach situation at the center of the convective cells. Here we have what we call an all regime situation. We then went to fully three-dimensional simulations of this same instability. Here we represent the convective cell with the velocity field in color. And we studied the low Mach correction effect on such simulations. So in order to do that, we computed the power spectrum of the kinetic energy that we present here for two simulations. One simulation using the low Mach correction in blue, and the other one when it is disabled, so set to 1. We observed that in this case, it has the benefit of getting more energy in the small scales due to the lower diffusion of the numerical scheme in a low Mach situation. And finally, we use this numerical scheme in order to study new convective instabilities. So this is a snapshot of a simulation run in the context of a grand challenge by Simon Daly on the Jean-Zé machine, or using 1,000 GPUs at a high resolution. And in this simulation, we use new physics using chemistry between the conversion between CO and CO2 coupled to radiation. So we use similar techniques in another context, a two-phase flow context, using the acoustic and transport operator splitting. So the situation takes place in a nuclear reactor, more precisely in the secondary circuit. So we recall that energy is coming from nuclear reaction from the primary circuit. It is exchanged to the secondary circuit. Steam is formed, and thanks to the turbine, it generates electricity. When the power of the nuclear reactor increases, it decreases the vapor quality in the secondary circuit, down to near 97%. So droplets of liquid form in this steam matrix, and at a velocity between 40 and 100 meters per second. And when there is a change of direction of the pipe, it can, when the liquid droplet hit the pipe, damage the material, as we can see here from the microscopic pictures. So the aim of this work is to study the pressure, the time evolution of the pressure at the wall during the impact of the liquid droplets. So in order to do that, we use again a compressible approach using the homogeneous equilibrium model that is written here. And it is seen as a relaxation of a 5 equations model. So we have here, in one dimension, 5 equations. So it can be compared to the previous set of equations.
Hello? Excuse me, the image is frozen for me.
Okay. So we have, again, the conservation of mass, conservation of momentum, and conservation of energy. So, and compared to the first set of equations, we add two more equations. So the first one is the volume fraction alpha and the mass fraction y. And in order to recover the homogeneous equilibrium, we have instantaneous relaxation source terms in which lambda is tending to infinity in this case to recover this model. We have also some closure relations to relate the two phasic quantities and stiffened gases as equations of states. So we use again, as I mentioned, an acoustic transport operator splitting. So the same idea to decouple the fast and slow material, the slow wave speeds. So we have again to discretize three subsystems: the acoustic, the transport, and this time the thermodynamics relaxation, in the case when lambda tends to infinity. But we use different numerical schemes compared to the first section. In this case, we use a relaxation adapted to vacuum in order to discretize the acoustic step, in order to get rid of a strong CFL condition that was related to the large density ratio that is happening here in the context of two-phase flows between the liquid and the steam. In the case of the transport system, we use an anti-diffusive solver in order to keep as sharp as possible the initial interface that is introduced in this physical situation. And finally, we use thermodynamics relaxation that is here to redistribute the mass and volume on a per cell basis and model the phase transition between the two phases. So the numerical scheme has the same structure as in the first section. It is conservative relatively to conservative equations with different fluxes for the compared to the first section. We here write the two acoustic fluxes, the velocity flux and the pressure flux. Here again, we can use a Loma correction in front of the diffusion term. And this time it involves the two speed of sound between the two cells at the interface of two cells. So we started by doing two-dimensional simulations of liquid droplet impact to compare it to a physical experiment. So the physical experiment takes place at 1 bar, and so at atmospheric pressure, and the droplet is placed in air. So the physical time sequence is the following. At the impact, a shock wave is developing and going to the back of the droplet. It is then reflecting at the interface between the liquid and air, and focusing at some point F where it triggers cavitation. In the case of our numerical experiment, that is a different settings adapted to the nuclear reactor situation. So it takes place at 30 bar and only involves liquid, only water. But we recover the same physical sequence. A shock is forming at the impact, going to the back of the droplet and reflecting, and forming this time a larger cavitation zone represented here by the darker region. When going to fully three-dimensional simulations, this time we use a deformed damaged wall, represented here in blue, with Gaussian perturbations, random Gaussian perturbations of the wall. Again, when the liquid droplet impact, we have the same physical sequence as in the two-dimensional case. The shock is reflecting at the back of the droplet and forming a cavitation zone that is here represented by the white region, which is the volume fraction. We here represent the pressure contours of inside the liquid droplets, and we notice that high pressures are not only located at the initial impact point, they are due to the inhomogeneities in the wall. So this simulation happened to be a grand challenge simulation that ran on the Joliot-Curie machine on the AMD EPIC RAM partition. Now, if we study the pressure evolution near the wall, that is here represented for 3 simulations. So in cyan, we have a reference that is an ideal wall, so no perturbation of the wall, and 2 simulations in green and blue that represent the case of a damaged wall for 2 resolution in order to check the convergence of the simulation. So we notice that the 3 simulations exhibit a peak pressure at the initial impact that can be related to the water under pressure that is given here. The pressure jump is given by the acoustic impedance times the velocity jump. But in the case of the damaged wall, we notice that we have unexpected secondary higher peaks that are due to the secondary jets that are colliding. So, in order to run the 2 grand challenges, we needed to use supercomputers and face the variety of architectures. As you can see on this drawing, in blue, we have the single-thread performance that is almost reaching a plateau over time, contrary to the number of logical cores that is still increasing, exposing more and more parallelism to the software developer. We also have, in supercomputers, a variety of architectures. An example is given here. For example, NVIDIA GPUs with the V100, or multi-cores from, for example, the Intel Skylake, and mini-core architectures with Intel KNF. So in order to be efficient on all these architectures, we chose to use the Cocos library that aims at implementing a programming model to write performance portable softwares. So it was extracted from a large Trilinos library that is developed at Sandia National Laboratories. It relies on advanced C++ features such as template metaprogramming and functors, and also relies on existing programming models. So, for example, OpenMP and pthreads in order to use the cores of CPU, auto-vectorization from the compiler, and also CUDA in order to run on the NVIDIA GPUs. They are also announcing more programming models in order to run on the coming supercomputers for the exascale. So, as examples, the AMD GPUs using the HIP programming model, and Intel GPUs with Cycle. They are also working on proposals to the C++ standard using, for example, STD MDSpan and BLAST operations. So, in order to be performant on these various architectures, Cocos introduces some abstract concepts. Here we have a representation of an abstract node of a supercomputer. Here we have, for example, the CPU with different cores in blue. To this CPU is attached different accelerators in yellow here. For example, GPUs or more exotic architectures such as FPGAs. And different memories that are located either on the die, on the accelerator, or the central memory. So to these different hardware resources, Cocos maps different software abstract notions. To these, they also introduce the execution pattern. So they are parallel fundamental algorithms. So for example, a parallel for, a parallel reduced, parallel scan, and tasks that will be used to build more complex algorithms, parallel algorithms, such as looping over the cells of our grid. They also introduce their own data container that is multidimensional and let the user control the internal memory layout. So in the case of the code ARC and forks of it, we use an hybrid parallelism approach using MPI and Cocos. So MPI is used to run on different nodes, and on one node we use Cocos. So the MPI parallelism is based on a standard approach using a domain decomposition. So we divide the total grid, and in each subgrid we assign it to one MPI process. And we use then a regular glacial pattern in order to communicate information between the MPI processes. On one node, we have different resources, cores and accelerators. We then use Cocos in order to attach to assign a line of cells in the subgrid to a team of threads. And the line of cells is divided into chunks, and each chunk is assigned to a thread. So here we have an example of how to write a computational kernel for Cocos. This is the function call operator that we need to implement. Cocos gives us a team of threads, and we assign it some work using this approach in our case. So we run different performance portability tests, and we represent here the performance in terms of mega cell updates per second, so in the context of a grid update. For ARC and ARC2, which are two versions of the code using different execution policies. In the first case, the range policy, and in the second case, the team execution policy. And we have two different architectures, the Intel KNL and the NVIDIA, the GPU. And we see that using a more adapted team execution policy, we can increase the performance on the Intel KNL, which is highly relying on vectorization, without decreasing the performance on GPUs. And then we went to scaling test. So in the first case, a weak scaling test on the GPU machine on Janzé, over 1,000 of GPUs. So in this test, we assign the same workload to each GPU, and we increase the number of GPU. We expect that the time to get to the solution remains the same. So the perfect case here is is an efficiency of 1. We also did a strong scaling test. Contrary to the first one, the total workload is fixed, and we assign to it more and more resources in order to decrease the time to solution. So the ideal case is here represented by the black line. So we have seen a way to increase the time, to improve the time to solution using parallelization. And now we want to use another approach by decreasing the arithmetic intensity using higher-order methods. So let us first define these higher-order methods. So if we take U to be a smooth solution of a conservation law, we say that a scheme is at order P if the truncation error is scaling as the spacing step to the power P. We say that we have a higher-order method if P is greater than 2. Usually, these methods are used to increase the precision at a fixed number of cells, but in our case, we want to decrease the cost of the computation. So there exist various methods that are usually based on polynomial reconstruction, such as, for example, the Ueno or Eno methods, in which we reconstruct a polynomial in the cell using the neighborhood. In the three other solutions, which are called spectral methods. Each cell is assigned a set of degrees of freedom, and these degrees of freedom are used to reconstruct the polynomial, and this time do not use the neighborhood. This is the case for the well-known discontinuous Galerkin method, which relies on the weak formulation of the conservation law. In this case of the spectral difference methods, they rely on the strong formulation of the method of the conservation law. And finally, we chose the spectral volume method. This time, that is relying on the integral formulation of the equation. And the degrees of freedom are, in this case, called control volumes. As it was originally derived, it was quite costly because it involved many quadrature rules. So let us introduce this method. We represent here two spectral cells. They are composed of control volumes called omega, and we want to reconstruct a polynomial over this spectral cell that is called here US. And we need to provide a numerical scheme in order for each of the control volumes. So here written in a semi-discrete form, and we need to define this numerical flux. So the first stage is to reconstruct the polynomial, and to do that, we use the data that are assigned to each of the control volumes by expressing that the polynomial, the mean value of the polynomial, is equal to the data inside, to the value inside the control volume. So we have now a polynomial over the spectral cell, and we are now able to evaluate the flux function at every point in the cell. So in the original method, they use quadrature rules at the order of the method to compute the numerical flux over each interface of the control volumes. This is costly as it involves many evaluations of the flux function and, as I will say later, many Riemann problems. In our case, we use a different approach by using a Lagrange interpolations over lines, here in pink and cyan. And we are able to integrate over each of the interfaces using this reconstruction. In the case of external faces, in yellow, we have two different values of the flux function a priori because of the discontinuity of the solutions. And in order to recover a unique value of the flux, we use a Riemann solver, an approximate Riemann solver. And again, we use Lagrange interpolations and exact integration in order to recover a numerical flux. And thus, this numerical scheme is well defined. In order to accelerate the simulation, we begin with a finite volume mesh, here represented in white. In a standard approach, we would reconstruct, using a higher order method, a polynomial over each of the finite volume cells. But in our case, we build a secondary grid, a spectral grid, by aggregating finite volume cells to form spectral cells and the control volumes that are attached to it. We can do a mapping between the two grids and assign values to each of the control volumes. We are now able to use the previously defined numerical scheme over the spectral grid and get a high order update. We do not use any a priori limitation, as it would smear the discontinuities over a spectral cell, big spectral cell, and also high frequencies of the numerical solutions. Instead, we use an a posteriori limitation approach that is a one-stage mood approach. So based on some criteria, if the high order method fails, we throw the solution, go back to the finite volume mesh and use a robust numerical scheme that is applied in each of the finite volume cells that are associated to the bad or invalid spectral cell. So as we changed the way to compute the numerical fluxes, we had to check that we had the correct convergence orders. So here in the isentropic vortex case, we plot the density error in function of the number of spectral cells, and we see that we recover the correct orders in the case of when the mood approach is disabled. When going to a more stressing test for the numerical scheme, in the case, for example, of the Mach 80 jet, which is a test case in which high velocity jet enters at rest matter. So we have in the upper part density and in the bottom part the valid cells. So in yellow the valid cells in terms of spectral update, and in purple the cells that use the fallback scheme. So we see that the fallback scheme is mainly used near discontinuities, so shocks, and also high frequencies of the solution. We can get to roughly 3.7 megasolar days per second using this scheme, which is roughly the Messer-Lemcock numerical scheme on the total grid. And if we go to, if we use another time integrator than the order flow, we can go up to 7 megasolar days per second. And finally, we present here two interface instabilities. So in the Kelvin-Helmholtz and Rayleigh-Taylor instabilities. So in the first case, for the Kelvin-Helmholtz instability, we have two flows with opposite velocities, and this triggers the formation of vortices. So the initial flow is here represented with the white arrows. And we see that the interface is taking more and more place over time in the simulation box. In the case of the Rayleigh-Taylor instability, which is dense matter over light matter, and due to gravity, this equilibrium state is unstable, and adding a perturbation breaks this state and triggers the instability. And also in this case, we have more and more the interface is taking more and more place in the simulation box. This raises a difficulty for this type of scheme, as the fallback scheme is more and more used and decreases a bit the performance. As a conclusion, we have adapted the acoustic transport operator splitting to two situations. In the first case, the astrophysics context, we used a hydrostatic, well-balanced numerical scheme in order to study convection simulations. We also studied the Lomax correction effect on idealized convection settings. We also use this splitting for two-phase flow in the context of two-phase flows using a homogeneous equilibrium model. We tackled the issue of performance from the parallelization point of view using COCOS and explored different execution policies. And finally, we also used a hybrid numerical scheme to improve the time to solution by decreasing the arithmetic intensity. We did not mention in this presentation the work of the port of additive module from the Ramses numerical code to GPU using Trinos, and also the implementation of the 2D case of the all regime scheme in Diablo, that is a prototype for AMR using COCOS. To this work, there are different perspectives. A first perspective would be the usage of the extension of the well-balanced numerical scheme to high order. more testing of the implicit scheme for convective simulations to be ready for production, the improvement of the equation of state in the case of two-phase flows. In the context of high performance, the improvement of the vectorization, of the reliability of the vectorization using the COCOS SIMD wrapper. And finally, in the context of hybrid numerical schemes, testing different fallback schemes. So using the think approach or anti-diffusive solvers that are usually meant for two-phase flow, the parallelization of the hybrid scheme mainly in terms of shared memory parallelism, and finally, the coupling of this method to AMR, as the refinement could be located near discontinuities or high frequencies, and the higher the representation of the solution in smooth regions. And thank you for your attention.
Thank you very much. So it's really nice that you keep your time on.